Hi, everyone. My name is Kohlmeier. I'm a senior software engineer at AWS Elemental. I've been working on video encoding for about 7 years now. Tonight, we're here to talk about encoder sync and the traditional way that's been solved by the industry, which is timecodes, and a new way to solve that, which is video alignment. And so before I jump too far into the slides themselves, the goal for tonight is to kind of familiarize all you with the concept of encoder sync, and then also with how we can replace timecodes with video comparison. So the goal of encoder sync is specifically to make the best experience for the customers. It's to have the cleanest playing video. Specifically, what I'm interested in encoder sync is when you're playing video, you don't see any jumps forwards or backwards. You've seen it when you're streaming from the internet. You're watching a sport event and it jumps forward a couple seconds and you miss something, or jumps backwards and you miss something. And if it's the World Cup winning goal and you miss that, you're going to be angry. And so the real goal for what we're looking at with encoder sync is to prevent that. So with that said, I've got a demo that shows what happens when it goes badly, and we'll show this demo twice tonight. So the first time, what we've got is a file that's being fed in over the internet to two different encoders that are feeding a single packager. And that packager is basically able to do redundancy with those two encoders. And if one of them fails, it will switch to the other one. I'm recording a player. That player is going to show basically just a backwards discontinuity, which means it's going to jump backwards because when it's failed over, there's latency. So that's the most important thing probably to call out, is that I've added latency to the input to one of the encoders. And specifically, I'm just going to stop one of the encoders as it's going. This is a recorded demo because I didn't dare chance doing it live. So at the timecode in the top corner of 234, it'll fail over. The two encoders are attempting to do sync. They're not going to be able to succeed because I have stripped the timecodes out of the input file. But I did burn it into the video just so it's really easy to see the jump backwards and the timing. So the lady will be waving out of her window, and then it'll jump backwards, and she'll be waving out the window again. Right there. So hopefully you caught that. I'm hoping it was obvious in the thing here. I missed it looking sideways, actually. So we're trying to avoid that because obviously if our customers see that kind of jump during a major event, they're going to be unhappy and angry, and their viewers are going to be up in arms, and maybe they lose rights to broadcast these big events again. Who knows? So we really want to avoid that. Now, what does this look like in terms of an actual production environment? In a production environment for these big events, you're going to see massive redundancy. You're going to see dual contribution encoders feeding the cloud so that if one of them goes down, you don't have an issue. You're going to see different regions or different networks involved so that if one network goes down, one region goes down, you, again, don't lose it. You'll have encoders in different places for the same reason, dual packagers in different places for the same reason, and finally, you'll have as much redundancy at the CDNs as the customer wants to support. And so in this example here, we're currently viewing a single route that goes along the top to a viewer, but if something goes wrong, an encoder goes down for any reason or something like that, you need to be able to fail over and you need to be able to find a new route. But if you look at this route's completely different besides the packager at the end. And so what's implicitly being stated here is that everything along the system here has to be functionally equivalent at basically all stages in order to have true redundancy going on. If you don't have that kind of equivalent setup, you're going to see the kind of artifacts like a forward or backwards discontinuity or something else. So from the player, what's really happening though when we're talking about encoders and their outputs is most players use segmented inputs to them. And what that means is they fetch segments of the live broadcast that's going on and pull them down and maybe pre-buffer a couple seconds. And they keep reaching out and grabbing them as they're available. But for it to be a good experience, you need that continuous stream to be fully represented inside of the segments, which means you can't have any repeat in the segments and you can't have any gaps in the segments. You just need a continuous stream. So when we're talking encoder sync, our goal is interchangeable segments. So in this example here, I'm just showing how if you were to fail from encoder 1 on segment A to encoder 2 on segment B, you'd still have that same original segmented experience without losing or repeating any content. What we saw a moment ago is essentially this. You'll notice that segment A and segment B have the same content because encoder 2 has some latency. And without some method of synchronizing the encoders and synchronizing what they're outputting, you'll end up with switches where you get repeat or gaps in your content. So I've mentioned latency as one of the many causes of these kind of sync errors, but there's a bunch of different ways you can get there. One could be input errors. So if the two encoders are consuming the same input, but one of them is losing frames on that input, then over time you'll start drifting, and you'll need to resynchronize. And I should say right now, because I'm going to keep using the terms interchangeably, there's initial sync and resync. Initial sync is when you're just starting up, and that's the first time you sync. Resync is when you're running for a while and in the situation I just described, drifting, and you need to realign. So another example is discontinuities, where your input stream might jump forward or backwards a great amount. And then finally, even if everything's perfectly timed and you've got zero latency, and your encoders are encoding the exact same frames at the same time, there are output types where if they start at different times, they're expected to start from different segment numbers. And so if there's no form of synchronization between the encoders, you'll get poor behavior just because at 10 seconds into your stream, encoder 1 might be on segment 10, and encoder 2 that's just started up might be on segment 1. And even though you're perfectly encoding the same frames at the same time, you're going to have sync errors there. So the next thing to talk about is how is the industry currently solving this, and the answer is timecodes. So a timecode is just a highly accurate clock. It's designed to be frame accurate. You can insert it on your input stream, and it's represented in the format hour, minute, second, frame. And the reason I'm telling you all of that is because the next couple slides are going to show timecodes, and I need you to know essentially what we're talking about. So sync is really about communication between the encoders. So in this example, I've got encoder 1 that's just now starting up and encoder 2 that's been running for a while. Encoder 1 looks at the input stream and looks at the timecodes that are embedded in that input stream and goes, the frame that I'm first seeing at this moment in time has this timecode. And I've got an example here that's 126, 13, and 29 frames. But the other encoder has been running for a while, and it's already been conditioning segments and outputting them. And so it communicates with that encoder, and that encoder basically says, the last segment I was processing had this timecode at the start, and it had this segment number. And so our first encoder, who's just starting up, looks at that and goes, all right, I'm in the middle of a segment. I can't start right now. I have to wait a little bit so that I can actually land on the edge of a segment, and then I'm processing at the same rate with the same segment number, the timecode that was processed in my partner's segment number. And this is that exact same example, just shown as segments. So you can see in the top, we've got a partial segment that's being dropped. And again, it may not be initially obvious why you need to drop partial segments, but imagine you're a packager, and you're just packaging whatever's arriving as soon as it arrives. And encoder 1 maybe sends that partial segment before encoder 2 sends the full segment. But the full segment's the full continuous stream from when it started, hours ago. And so you can't send that partial segment because it'll cause problems. And so the first place where we get synchronized is when we get to our first full segment, and that's when we start emitting when we're doing our initial sync. And obviously from there on, the goal is to have perfectly interchangeable segments. All right, so if timecodes are so great and allow sync, the next question you gotta ask is, why do we have to move away from timecodes? Why aren't they good enough? And there's a whole bunch of reasons that they're not great. One, you might have a legacy broadcast system. You may not have timecodes set up. And if you're in that state, it might be incredibly expensive to install and maintain, not just in terms of the devices themselves and the cost, but the person headcount in order to actually fund making sure those work and are maintained correctly and debugged. And debugging is difficult. You've got 30 frames per second coming out of your camera. You've got 30 frames per second coming out of your timecode, and they're drifting. Over time, you're losing a frame of timecode, or you're repeating a timecode. How do you figure out if it's the camera or if it's the timecode inserter? We've got partners who frequently don't have control of the video content they get. They may have affiliate stations or something else going on that are giving them content, but they can't control how that content's generated. And when that happens, they often don't have the option to insert timecodes. And one of the things I didn't tell you about timecodes is they don't just have to be hooked up to the camera. They can be hooked up in many places. They can be inserted in many places. The contribution encoders, which aren't synchronized, can be inserting them. And if there's no latency, maybe that works. But at the same time, if there's even a rounding error on the wall clock time you're using for those timecodes, maybe it doesn't work. Maybe you're off by 1 permanently. And also, timecodes don't actually examine the content, so when it is drifting, you have no idea that it is drifting. All right, I'm talking fast. All right, does anyone have questions up to this point before we hop into video alignment? Okay. So the goal for the video alignment section isn't to deep dive on all the portions of the algorithm that we're trying to implement. It's to walk you through the concepts and make sure you have a solid understanding of what we're attempting to do. And so the first thing you should know is from here on, we're not really going to talk about the output. We're going to talk about the input. Because we already have an alignment algorithm that works with timecodes. And timecodes are just kind of fancy numbers that let you say, this frame is this time, and if I compare to another stream, I can find that frame and tell you when it's being played. And so what we're really looking for now is a replacement for timecodes. And so I'm going to talk about how we find a replacement for timecodes on the input rather than how we condition the output, because everything that goes into the output, it's just being a replacement. It's the same functionality, it's just a new way to align them with a different system. So with that said, to a human looking at the input stream, when you've got these continuous frames coming in on stream A and stream B, if you're looking at timecodes, it's really easy to see how you would align them. Quite clearly, 10 aligns to 10 with an offset of 2, and 14 aligns to 14, again with an offset of 2. So conceptually, with timecodes, you understand how we're aligning. I think in the same fashion, when you do this as a human looking at real frames, it's easy to see how you do alignment. Now, I've added alphanumeric in case anyone's colorblind, but I think visually it's easy to see the blue aligns, the red aligns, and the various shades. Maybe not quite on this projector, but they do align with the same offset of 2, and if nothing else, on my screen, I've labeled all the colors with the same letters. So this is the basic idea that if I as a human can recognize transitions in video and the clear shapes matching up between video at various points, then why can't I teach an algorithm or create an algorithm that can do this? All right, the first thing you need to know is still about communication, but instead of communicating timecodes, we're going to communicate about the frames. So this is a parody of the slide we had before, and basically, you can see that instead of communicating a timecode, we're communicating frame data. So instead of saying, I've got this timecode at start, I'm saying I have this frame at start, in this case, the purple frame at start. And my partner encoder is going to say, I processed the light purple, the kind of flesh-colored, and the blue all into segment 245. And we're going to take those frames and that information about the segment, and we're going to look in encoder 1 at the frames that were processed and go, great, I can find the frame that I'm processing and figure out where it should align, and I can therefore figure out I need to drop and again wait to the edge of some segment. So here's how we do that though. The first change here, and this is a pretty dense slide so I'll be here for a minute or two, is instead of saying encoder 1 and encoder 2, we say leader and follower. And the reason for this is our leader is going to send information to our follower, and our follower is going to align to the leader. And I hope that's clear enough now. The next thing to notice is I've added frame IDs to every frame that we're processing. So the leader started just before the follower and started labeling the frames. Now, the IDs are not labeled the same across our leader and follower. They are labeled differently because it's based on the order that the encoder is consuming them on. So where G is 1 on our follower, G is 4 on our leader. And finally, I'm showing that we're storing a kind of a window of time, the most recent n number of frames that we're processing, in order to have kind of a window that we're trying to match between the leader and follower. But we are only currently encoding the H and I on the leader and follower. And finally, because it will matter to one of the later slides, there's a single frame of latency going on right now, where the follower is 1 frame ahead of the leader in terms of when it's processing frames. All right, so we've received a new frame on both the follower and leader, and the first thing that happens is our leader communicates frame information about that frame, enough to do some matching to the follower. I say information, it doesn't have to be the full frame, you just have to find enough information to communicate that you can still do some amount of comparisons successfully. Obviously, transmitting every raw decoded frame would be incredibly expensive. The next thing to notice is the follower, before we talk about how it processes, is just going to store all of the leader data, which is why I've got the smaller queue below it showing that the follower is holding data from the leader that it's been transmitted. All right, what does it do with this data? The follower is, as I stated, going to try to align to the leader. And what that means is it needs to figure out what offset it is to the leader currently on its local frames so that it can adjust the ID it associates with its frames as it passes that information downstream to our synchronization algorithms. And so what it's going to do is it's going to take that new frame from the leader, frame I, that was labeled 6, and it's going to compare them with all of the follower frames that have been processed in our window of time. And it's going to find its best match. So in this case, it's really clear and easy as a human to see that I matches I. Obviously, frame comparison is a challenge, and there's a lot of different algorithms you can try, but in this case, we're doing frame comparison, and I matches I. And we go, all right, our best local match is 3, so now I'm going to calculate my offset for that match, which is the ID of the leader frame minus the ID of the follower frame. So my offset also happens to be 3. So great. Maybe with just one offset I can go, I know what I'm doing, and I should immediately assign 3 as my offset to all of my frames and adjust my values and start sending things downstream. Obviously, it's not that simple, and we're going to talk about that. The next thing we have to do is we also compare the local frame we just got, the frame that the follower is processing, J. It's J because it's ahead of the leader by 1 frame. It's going to process all that leader data, and it's going to figure out its offset. Now, the leader hasn't processed J, which means we're not going to find a best match for that frame right now. The best match we're going to get, though, well, we're not going to find the exact match. The best match we will find is I still, but that's not an exact match. And so this time when we do our calculation for offset, it's still the leader ID, which is 6 still, minus the follower's frame that we're comparing, which is 4, which gives you a 2. Now, the problem here is we got 2 discrepant pieces of data. Now you're saying my offset should be 2, or it should be 3, and how do you know which one to trust? Also, the situation could have been reversed. The leader could be ahead of the follower, and now we're not getting perfect matches on that first comparison of the leader frame. So what we do is we store all the offsets we've generated in our window, all of our best matches, and we pick an algorithm. I'm just showing an example right now of least squared in order to take a data set and find a trend. So in this case, I only showed a pretty simple setup, but I've got a single value at 4, while all of my other offsets at 3. And clearly the least squared algorithm is trending towards 3. And so at this point in time, now I've got a history of data, and I've got a number of consecutive kind of offsets that all trend towards 3, and I can go, oh, okay, I clearly do have an alignment, and it's an offset of 3, which matches the values we had before. And from here on, I can assign all of the follower frames the same ID that the leader frames had, and use that with our traditional syncing algorithm, where we're looking at what frames we're putting in the segments on the output so that we know that they are aligned. It's still not that simple. There's some difficult and challenging situations that we should go through. The most obvious is what happens when you've got repeat and black frames. When every frame that you're comparing on both of them is exactly the same, every offset you're going to get it is going to say that, yes, any of these frames can match. They're all equally good. And so there's not exactly a solution where you can align here. But the principle we're following is be the least disruptive, do the least damage. And what that means is if you've got a good offset going into black frames, keep using that offset until you've got a clear indication, again, that you've got a new offset and you need to change. Don't just change just because you can't find a good match or because your algorithm no longer has a clear trend line. This is another situation where it becomes difficult. Your input has dropped a frame on one of them, but not on the other one. And really this slide is emphasizing the need for a good history and not just a small window. And it's a real art to picking how much time you should compare, and I don't have the best answer. We're still trying to figure this out. But when it drops a frame, you can see beforehand, before G was dropped, that the alignment offset was a value of 1, because E and E align 2 and 1, that's an offset of 1, whereas H and H after G is an offset of 0. And so what this is emphasizing is that after it changes, even when it's correctly changing, it will take you a period of time to get enough consecutive offsets to know with confidence that you should change. And I guess I should explicitly say that means there will always be a little bit of latency in terms of when your offsets change because of errors or input switches or something else, and when you're successfully going to realign. Whereas with timecodes, it's instantaneous because the second you go from 24 to 28, you know that 4 of the timecodes were dropped. All right, this last slide is kind of a comparison of the two. The first bullet, I hope, is really obvious. Video sync doesn't require any kind of timecode. Timecode sync does. Video sync actually looks at the video content and can determine when you've got problems, whereas if there's something wrong with your timecode, you have no concept of that. There are times also for video sync where you're not going to be able to match, such as the black and repeat frames, or if your content is entirely not matching at all. You've done an input switch on one encoder and the second encoder has an input switch as well. And finally, the latency of changing that I just talked about. Timecodes, of course, have the benefit of instantaneous reactions when they change. You know they changed and you immediately can react. On the downside, they're expensive and painful to debug. Back to our bookend demo slides. This time, it's the same demo. It's the same 1 second delay. It's the same encoder 1 getting cut off. And the demo is not super exciting because all you see is continuous video. I should say one thing for anyone watching on YouTube, pausing and checking in again. I didn't realize when I was recording, I converted the frame rate from 50, I believe it was, to 25. And so if you're pausing every frame, you'll see it skip timecodes forward every other frame because we're dropping every other frame. I apologize for that, but just in case YouTubers are watching and going, what the heck? So anyways, same video, again, around the 30-second mark, the 2:30, that is. It is got a interruption, and yeah. I'm happy to start fielding questions now if people have them, but you won't see anything. It's just going to continue. I don't believe you.
Nice.
Okay. Questions? All right. Mike for Mike.
Thank you. So please describe what happens when one encoder goes away, like its instance fails, and then you need to replace it. How long will it be until you have a working system again?
I was hoping I'd get more questions in the middle, which is why I didn't include that slide, and I probably should have prepared a backup. The question is, what happens if your leader, I assume, crashes? The follower, of course, will always be able to find its new offset to the leader, but if the leader restarts, you probably start counting from 0 again. The solution that we're looking at is making leadership dynamic. So that if there's problems, you can change.
Oh, I was already assuming leadership was dynamic. I'm sorry. I was assuming leadership was dynamic. I didn't understand that that wasn't the case already. So once leadership is dynamic, how long will it take for a follower to reintegrate itself?
It takes about the same amount of time as when you first achieve sync, because you need enough frames. So, I mean, once both encoders are back up, it takes about the same time as initial sync in order to get that, which is the same amount of time that you're...
So if the leader happens to die during this point, you're kind of out of luck.
Again, I would say that if you stop seeing your information from the leader coming, you should follow the same principle as the black frames and don't make changes. Are you imagining a system where you're doing n encoders? Like a whole bunch of encoders?
I'm saying let's say you have a chaos monkey in here that's killing your instances, and it happens to kill 2 encoders within like a second of each other, and they happen to be in a leader-follower type of situation.
I see. Yeah, yeah. Essentially, you can end up out of luck because the latency of your video frame comparison, the amount of time that it can take means that you won't have any input content that matches the input from before your window of time. And so unlike timecode, where you obviously have an actual number that's very easy to resynchronize, in this case, yes, it's incredibly challenging then to figure out anything.
Right. We've come a long way from interleaving encoders with different bit rates just in case one failed, haven't we? You guys remember that?
Question is around communication. How is that established? When I think of failover and multiple, I think of multiple data centers, not just. So if I wanted, the Super Bowl, everybody's favorite example, multiple continents, can the communication, what's the latency?
I mean, it depends on what type of communication you choose.
I guess is it reasonable is my question. Is the latency of potentially a cross-ocean?
If the latency is greater than your window of comparison, you're going to be in trouble, right? So if you're using a fraction of a second of comparison and your latency is a second, you're going to have problems. But if your latency is a fraction of a second, like if you're within the US, it's pretty quick, right? So if your latency is very short and you're using a reasonable window of time, 20 seconds or something, to do comparisons in, then you're going to have some ability to lock even if it's in the past, right? Because you're not again, you're storing, sorry, I moved the mic too far. You're storing the history of all the frames, both the leader and the follower. And so even if you're some amount of time behind, as long as your window's large enough for comparison to support the latency, then you should be okay. You should be able to find a match.
And I guess my next question is, do you need to sync every frame, or do you need to sync the first frame of a GOP or segment?
You need to ensure the segments are synchronized, right? So you don't have to be syncing every frame or everything else, but for video comparison, it's really challenging. So imagine you're doing exactly one file input and the encoding is exactly the same. Great, your GOP cadence and everything else is exactly the same. That's really easy to match. But if you're using two contribution encoders that were started side by side, and they started on different frames, and they're encoding at different cadences with different encode artifacts, you may have more challenge if you're just trying to use that first frame of the input rather than all the frames.
Because you use the example of a drop frame, and most encoders you set like a fixed frames per second, so it would just dupe a nearby frame on either side generally. So
you'll find a nearby alignment, but because if one encoder has lost an input frame, there's different ways to recover. Sometimes the encoder will repeat frames or something like that, right? Other times, if it's a large enough discontinuity, you've lost enough input, you have to perform some sort of time resync, right? And so it depends on how bad your loss is, whether or not that single drop will require a change in the output, or whether the alignment will be able to maintain.
I promise this is my very last question. The scenario I'm thinking there, you have two separate data centers and your leader is having packet loss, right? And that's why you lead to dropped frames. The follower is now going to recreate those artifacts. Like you can end up in a scenario that you kind of want the leader or the follower to just, it has all the frames, right?
Sorry, I didn't quite follow the granularity of what you're asking.
Okay, so let's say every third frame is dropped by the leader, right? Yep. The input coming in, it's having some sort of packet loss. It's losing a frame.
Yep.
The other data centers, network's totally fine. So it's getting every 30 frames every second.
Yep.
And it seems like the algorithm says this is the leader and it's dropping every third frame. Is it going to cause the follower to drop every third frame?
This is a good question that I don't have an answer to right now.
Okay.
We're working on it.
And I will say it's a great idea because it will just work.
Clearly, there are situations where this will help customers. There are still hard things to work through.
On that, maybe fail over to the change leader follower faster or something. I don't know, but Aaron, my question is there anything about? It didn't seem like, but is there anything about this that the leader and follower in different AZs versus leader and follower in different regions? Is there, it works
Is the
equally either
latency
way,
on
right?
if your latency, there's not a good reason if your communication can go cross-region that you shouldn't be able to do cross-region.
Right. Is there some kind of latency threshold that you're seeing, or?
It's really based on the buffer window size. If you set your window size too small and you need, let's say your window size is 2 seconds, which is really fast, and your latency is 1 second. If you need at least a second and a half of overlap, you're going to have a problem, right?
Okay.
So it's about how big you make your window and how much latency there is in your communication.
Got it.
And also on your encoders to start, because obviously it's not just latency in your communication, but if one encoder is behind the other encoder by 3 seconds, then that adds an additional latency on top of the communication.
Gotcha. Thank you.
Any other questions? All right, great talk. Let's give a round of applause. That might have been our longest question session yet, so that's good. That means people are thinking. Let's go ahead and take a little break.